So welcome to all of you. Let me just start with some introductions, general introductions about the meeting. So as I mentioned at the beginning of the session on Monday, so there is this, we have this grant called HeI Energy Intelligence, and the consortium is composed by Porto, which is the coordinator, Madrid, then Torino University, some labs in Paris, and NICEF. And the general proposal for this is to continue, let's say, on the bootstrap ideas, but also include integrability and some novel developments in machine learning and artificial intelligence. So this consortium can travel to various places outside Europe, which will be APFL the first year, then JLab, then Brazil and Perimeter. So this is so for today, so the proposal was organized into 3 work packages. Today we will listen about the first work package, which mainly focus on integrability, analytic conformal bootstrap, and S-matrix bootstrap. So we will have presentations from the various groups in the consortium. And work package 2 instead is dedicated to effective field theory for collider physics, and will be the subject of tomorrow. We will have a presentation by Ignazio Scimeni and Water from NICEF. And then work package 3 is something that we had already on Monday. For this, I just want to mention that we have a short-term goal, which is that of having a training. So get to know what's in the machine learning community, what's the methods, understanding them. And then there is a long-term goal, which will be to explore how to use this in theoretical physics. So let me just advertise that today in the afternoon, we will have a research talk by Michelangelo Preti and a research talk by Damien Leflotte on S-matrix bootstrap with machine learning. And tomorrow we will have a review seminar by Vladimir Brown on conformal symmetry and strong interaction. So I will keep you updated with emails, but please consider that today and tomorrow we have a number of activities. So with this, I would like to start the session of today morning with Vasco, which will give the first presentation, I think, about multipoints, a correlator, and integrability.
Okay, so hello everyone. So yeah, I'm the representative from Porto, and my talk today it's called Multipoint meets integrability. But what I want with this talk is more What I want with this talk is to show how Porto meets other nodes. As Francesco already said, this is a staff exchange program. And okay, I already prepared some slides that, okay, now they're not needed. So this is the consortium. You can go to this website to see some information about the consortium. We also have a website for another website for the consortium. And I guess I can skip this. And I will also mention something about the work packages that was not mentioned in the slides by Francisco. So as Francisco said, there are 3 work packages. One is about strongly coupled quantum field theories and the emergence of spacetime, and it's the topic of today. So in this there are the bootstrapability. There are 4 different tasks. There's the task that's about bootstrapability, that's going to be mentioned in Andrea's talk. There's the losing the straps in the conformal field theories. That's something that I want to talk today. There's also about a task about gravity reconstruction from CFT amplitudes. And I guess Francisco will tell us about this in his talk. And there's also a part about S-matrix and form factors bootstrap. And HeI is going to tell us about this. Okay, there's also the work package about EFT collider physics and partonic distributions, and that's the theme for tomorrow. And there's the third work package, which is about AI and machine learning in ING physics, and that we already learned on Monday. What I will try to convey in this talk is that Porto Node has some links with all of these tasks, and I guess we can also contribute to work packages 2 and 3. So this talk is about how Porto, so here's a picture of Porto, fits with other nodes. So after this brief introduction, let me tell you more about our group. So that's me, and this is Miguel. These are the more senior people from our group. And we also, our areas of expertise are conformable bootstrap, integrability, S-matrix bootstrap. There are some AI in physics. We also study energy correlators and Reggie physics. We have a postdoc, Pulgit Agarwal, and okay, I could not find a picture of him. And we have 5 PhD students that I guess you'll meet during our secondments. And these are our 5 PhD students. And these 5 PhD students, they work on these areas, and conformable bootstrap, integrability, S-matrix bootstrap, AI in physics, and energy correlators and Reggie physics. Okay, so let's now go to science. And I will start with conformal field theories. So conformal field theories, they are important in condensed matter physics and statistical physics. They are important in gravity through the ADS-CFT correspondence, as Francisco will tell you more about today. And they are also important in quantum field theory. So let me tell you a bit more about conformal field theories and why they are important. So in conformal field theories, we usually study correlation functions of local operators. And just by imposing symmetries, the symmetries of conformal field theories, you can see that the correlation functions of 2- and 3-point functions, they are fixed just by imposing symmetries. So this is the correlation function of a 2-point function, and it's completely fixed just by this number here that it's usually called the dimension. And the same happens for the 3-point function of 3 operators. It's completely fixed up to this number that appears here, and that we call OP coefficient or 3-point coefficient. So these coefficients see here. So these are some of the properties of CFTs. Another property that is very important in CFT is the operator product expansion. So the operator product expansion is this property that's related with the product of 2 operators being able to be expressed in terms of sums of operators just at a single position. What's really important here is that this part, this function f, is kinematical, and these function c's that appear here in front are the OP coefficients or the 3-point coefficients that already appear in the 3-point functions. And why is this important? So this is important because this implies that everything in a correlation function or in any correlation function in a conformal field theory is expressed in terms of this dimension and these OP coefficients that already appear in the 2- and 3-point functions. So, and why is this so? So the reason is, okay, and usually it's called the CFT data. So the reason for this is the following. So you can start with a correlation function of n points, and then you apply this property, and then again you get to n-1 point functions. And let me stress again that this function here f is kinematical. And okay, and then if you repeat this process iteratively, you'll get eventually to 2 and 3-point functions. And those are completely fixed in terms of these deltas and these c's. So once you know all these deltas and all these c's, you know everything that needs to be known about a correlation function of local operators. And yeah, please interrupt if something is not clear. So our goal, or the goal of the community, is to determine these CFT data. So determine these deltas and these c's. So one question that you can ask is this CFT data arbitrary? So what has been done in the past is to prove that this CFT data is not arbitrary, and this is the goal of this bootstrap philosophy. One way to get to this to answer this to this question is to start with a 4-point function of 4 local operators, which is not fixed by symmetries. So you start with this 4-point function, you apply that OP property, that operator product expansion, and you rewrite everything in terms of these sums of these c's with this kinematical function f, and then here you have a 3-point function which is completely fixed by symmetry. So this is representative pictorially in this picture. So you have the OP between the operators located at 1 and 2, and then you have here the contribution of a given operator that I've represented here by O. So this is one way to express the 4-point function. But here I've done a choice. I've done a choice of doing the OP between the pair of points 1 and 2. I could have done this in other ways. So I could have done this within the pair of points at 1 and 4. And this is represented in this picture. And this has to be equal. So this way of doing the computation in this pair of points in 1 and 4 and 1 and 2, this has to be equal. And this leads to the bootstrap equations, to the conformal bootstrap equations. So how powerful are these equations is what I'm going to show you next. So using these equations, it's possible to extract some consequences. So in a paper more than 10 years ago, so it was shown that these deltas, they cannot be arbitrary. So these dimensions of the operators, they are not arbitrary. And one way to arrive at these constraints is the following. So you start with a 4-point function of 4 operators that here are labeled by sigma. And then you do OP between these pair of points, sigma. And then you start to make assumptions. So you say that in the OP of sigma, there's the contribution of the identity, and then there's an operator that's called here epsilon. And this is the operator that has lowest dimension in the OP of sigma and sigma. And then you ask if the dimension of this epsilon can be arbitrarily large. And then you look at the bootstrap equations, and you get that if you get that this shaded region here, it's an allowed region, and in this right region, it's not allowed by the conformal bootstrap equations. So this tells you this is an example of the power of the consistency of the theory or the bootstrap equations. So, and the lesson here is that the dimension of this epsilon cannot be arbitrarily large. So are there other bootstrap examples? Well, there are. So you can use the bootstrap philosophy to constrain holographic theories of gravity. And I guess that's something that Francesco will tell us about today. And you can also use bootstrap to bootstrap gauge theories, more specifically in n equals 4, and that's something that Andrea is going to tell us about today. So in Porto, we have also used consistency conditions to determine holographic correlators. More specifically, in these papers, we have used these consistency conditions approach to determine holographic correlators of 5 and 6 point single particle correlators using a method, using a bootstrap method. And starting with these 5 and 6 point single particle correlators, we can do an OPE, or product expansion, and recover multi-particle correlators. That's going to be talked today by Francesco. So, and this is a link between the Porto node and the Madrid node. Okay, this slide is not good. So, so now what about integrability? Integrability, we'll focus on integrability in n equals 4. So n equals 4 is a conformal field theory, and since it's a conformal field theory, it's determined by the CFT data. And okay, n equals 4 is also a 4D gauge theory, which is another motivation why it is interesting. So, and since it's a conformal field theory, we can try to apply bootstrap methods to determine these CFT data. Okay, let me just tell you the status of integrability about these CFT data. So it's fair to say that we know more or less how to solve for these dimensions of all operators using integrability methods, at least in the polynomial element. So, and this is part of the CFT data that we need to know to get an handle on any correlation function in a conformal field theory. What about these OP coefficients? So these OP coefficients, they are partially known. And the best method that we can have using integrability is described in this picture, which is based on a form factor expansion that was presented in this paper by Benjamin Basso, Shota Komatsu, and Pedro Vieira. And let me stress that this P here is Benjamin Basso, which is in the Paris node, and Pedro Vieira is in the node of Canada. That's from perimeter. So the status for the 3-point functions is not ideally, and okay, for higher point functions, the status is even worse. Yeah, Francesco, can you tell me how much time do I have?
Yes, you have some until 12.
Okay, until 12. Oh, okay. So you mean that I have 7 minutes?
Yeah, because I gave some introduction.
Okay. So, okay. So the status for the higher point functions is even worse. And what is the status for the other observables? So, okay, other observables that you can study in gauge theories are Wilson loops, no polygon Wilson loops, and the best method is a method that was introduced by Benjamin Basso again, and Amit Sever and Pedro Vieira. Again, Benjamin Basso is from the Paris node, and Pedro Vieira is from the perimeter node. And okay, you could try to consider other type of observables such as energy correlators, and I guess that would be interesting for the node in ECAF. So and for these energy correlators, which are represented pictorially here, so there's no method using integrability. So here's here could be a challenge for the integrability community in this consortium. So the question and what I want to convey here in this part of the talk is can conformal bootstrap help in these problems? And the answer is yes. So you can see recent work from Torino and from the talk by Andrea. So, and from Porto, what we have been studying in the recent past is the following: is studying consistency conditions in higher point functions. So when you have, for example, a 5-point function, you can decompose this 5-point function in the OP in this way. So you do the OP between the pair of points 1 and 2, and then 3 and 4, and then everything is fixed in terms of, or expressed in terms of OP coefficients. And then you can also obtain higher point bootstrap equations. So this is one way of doing the composition of 5-point function, and this is equal to just needs to be equal to this decomposition. So here in the middle, you have a OP coefficient between these operators that I've called here O and O tilde, and these 5 that I'm thinking about being these external operators. So by setting these higher point bootstrap equations, what we have shown is that this can fix these OP coefficients. And what about 6-point functions? So we can also study these consistency conditions for 6-point functions. Here on the left, there's a particular decomposition of a 6-point function. And okay, there's this particular decomposition, and you can also decompose it in other way. Here I've chosen the pairs 1, 2, and then 3, 4, and then 5, 6 to do the OP. And here on the right, I've chosen the pair of points 2, 3, 4, 5, and 1, 6 to do the OP. Here in the middle, there's an OP coefficient between O prime, and O hat. And just by imposing these consistency conditions between these two decompositions, we can fix this coefficient, these OP coefficients in the middle. So one way that Bootstrap can help in integrability is to give integrability a target. So you can say what integrability should aim at, or what integrability should get after imposing these bootstrap constraints. So another way that Bootstrap can help is okay. I will have to go fast in this part. So there's a duality between null polygon Wilson loops with n sides and correlation functions with n operators. We can apply these bootstrap games for these correlation functions. And by applying these bootstrap games, in the past we have found a relation between these different formulations. For this particular one is for Wilson loops, and we found a relation between this other formulation that's for 3-point functions. So by playing a game between these bootstrap equation for higher points, we were able to derive some sort of relation between two different objects that are supposed to compute different observables. Here's a hexagon form factor on the left. Here's a pentagon form factor that is used to compute null polygon Wilson loops. Okay, so to the future. So to the future, we can also bootstrap we can impose bootstrap constraints in other topologies. This is a different topology, and this has not been done, and that's something that we aim to do in the future, and maybe we can also collaborate with other nodes in the HeI collaboration. So here on the left-hand side, I have these OP coefficients, O, O tilde, O at. And here on the right, I have these OP coefficients that appear. I'll call them here C mixed, because they are a bit different from these OP coefficients that appear on the left. So the main question here is what can this tell us about integrability? So other possibilities that we can do is talk about Reggie physics using the methods that we have developed here in Porto. But I'll skip this. So let me go now to discussion and future directions. So in Porto, we have focused more recently in holographic correlators and integrability. And recently I've been interested in two other areas, which are energy correlators and S-matrix bootstrap. So these holographic correlators and integrability, they have some overlap with the nodes from Madrid and Torino and Paris. And these energy correlators, they have some overlap with the nodes, for example, in ICAF. And we have also been starting to study S-matrix bootstrap, which has some overlap with the work that is being done in Paris. So with this, I will conclude.
Thank you, Vasco. Thanks for the introduction and the presentation. So maybe we have time for 1-2 minutes. Sorry, we have time for 1 or 2 questions.
Okay.
Maybe I can ask one question regarding the energy correlator. In principle, from N=4, it's somehow it's built in that you can do something with integrability, or
yeah, the thing is it feasible or not? In principle, so there's this approach to compute correlation functions with any point correlator, which is based on this hexagon approach. The thing is that it's very hard to do computations with that hexagon approach, starting with 4 points. So the 4-point function has not been studied in the hexagon approach for more than 1